So last lecture, we started with the simple harmonic oscillator problem. And a harmonic, so I'll just go through the lecture quickly in case you have forgotten, which is very likely. So in a harmonic oscillator, the characteristic is that the restoring force is proportional to the displacement and acts opposite to it. And if there are no dissipative forces, then this results in an oscillatory motion. Okay, so this is a general definition, and then the energy for this system has two parts: the kinetic energy, P squared by 2m, and the potential energy, which can be written in terms of the force constant K as half kx square, x being the displacement, or what is more suitable for the solving the quantum problem is to write it in an alternative form as half m omega square x square, where omega is the angular velocity of the motion. We borrow the form of the potential from the classical problem to form our quantum Hamiltonian for the harmonic oscillator. And then we proceeded to solve it in a very unique way. So this is not something that you would usually employ as a method of solution, but it is particularly useful for the harmonic oscillator problem. So the thing is, we've tried to factorize the Hamiltonian into two operators, which is written as V dagger V, and this is by construction Hermitian, and we find out the form of V. So to do that, we simply factorize this into a product of two quantities. So a square plus b square can be factorized as a plus ib into a minus ib, and then we found the operator forms for this, but it was not, so the Hamiltonian we saw was not exactly factorizable. There was an additional quantity which involved the commutator of x and p, but then that is a constant, so that is no problem. And that helped us factorize the Hamiltonian as a product of two quantities of the form V dagger V, like we were aiming, plus a constant. Okay. We also found that the operator V is Hermitian. Okay. No, did we do that? No. Anyway, so then once we had the Hamiltonian in terms of V, we wanted to simplify it further. To do that, we first explored what the commutator of V and V dagger was, and we found that it was again some constant 2h cross by m omega. So we split this quantity between V and V dagger so that the commutator turns out to be 1, and we redefined the operators, and we got some new operators as A and A dagger. So we got A from V and A dagger from V dagger, and then my A dagger commutator turns out to be 1. This is useful because we will deal with strings of these operators, and the simpler the constants, the easier it is to keep track of them. So A and A dagger can be written in terms of the x and p operators, and alternatively x and p can be written in terms of A and A dagger. But the beauty of this method is that you don't need the explicit forms after this. So just some properties of A and A dagger help us to solve the problem. Okay, so then we rewrite the Hamiltonian in terms of A and A dagger, and it looks particularly simple. But now what we see is the Hamiltonian, when we use the Hamiltonian to act on psi, then we need to know what the action of A and A dagger on psi is. To do that, we first see what happens if we have a function that is A psi. Then if we apply the Hamiltonian and we use this value of the commutator, that is the only thing that we use, then we see that A psi is also an eigenstate of the Hamiltonian, but it has an energy which is h omega below the energy of psi. So E minus h cross omega is the energy of the wave function A psi if E is the energy of psi. Similarly, if we use the Hamiltonian on A dagger psi, we get an energy eigenvalue which is h omega above the energy of psi. So what we're basically getting is different eigenstates of the Hamiltonian once we know of higher and lower energy, once we know some psi. Okay. So the idea is now to find one solution of psi. And then we can use this idea of shifted energies to obtain the energies for the other functions. Okay. Now, in some previous lecture, quite some time back, we showed that the energy of a state can never be lower than the minimum value of the potential that is in the Hamiltonian. Now here the minimum value of the potential is 0. So in the first place, the negative energies are disallowed. So once my energy of the state hits 0, the wave function must disappear somehow. Okay. Eigenstates with negative energies will not be valid. So using this condition, this is called the annihilation condition, we say that the lowering operator acting on some lowest function, psi 0, which you can call the ground state function, will eliminate the function. So it will annihilate the function. And using this, we bring back the explicit form of A. That is the only place where we need to bring it back. We get a simple first order differential equation, and we find psi 0 from this equation. We also gave some additional arguments why this annihilation condition is valid, but I will not go through that now. Okay. Then when we solve this first order differential equation, we get quite a simple form for the ground state wave function, and the normalization constant can also be obtained quite straightforward, in a straightforward manner here. Okay. Now this is where we stopped last class. Let me just check how many are here. Okay, we are fine. So we stopped here, and we wrote a general form for the energy of each state as n plus half h cross omega, and we found a general form. We didn't find it actually. I just stated that the general form for the normalization condition for any excited state is 1 by root of n factorial. And to obtain this excited state, you only need to operate a string of A daggers on the ground state wave function that we have found. Okay. Now, if you want to find something that looks explicitly like a wave function, like a function in x, then you have to, of course, open up the A dagger into its x and p form and actually operate that. But p, the only thing you will need to do is differentiate because of the differentiation operator in p. So that's not a very difficult thing. So you can just differentiate this as many times as you like, and you will get the explicit form of the wave function if you ever need it, but you normally do not need it. Okay. Now we shall look at some additional properties of these A operators, which are called either creation annihilation operators or ladder operators, raising. So and then A dagger is called a raising operator, and A is called a lowering operator. So these are just different names for A and A dagger. And so the first property that we look at is what happens if we act A first on some general psi n state and then A dagger again. So you lower it and then you raise it again. So what happens? So, okay, so I have expressed psi n here in the full form that we wrote here with a string of creation operators for the nth state. And then we use the fact that A dagger commutator is 1. So I can so what I have done here is I have moved A to have moved A, and then I have got this expression in terms of A daggers. Okay, and then what happens is I get back my psi n with an additional factor or a number of n. So n will come from summing 1 n times. So I am moving A across this whole string of operators. Okay? And every time I move it across one A dagger operator, I will get a constant 1. And I will keep moving it, keep moving it, keep moving it. And then finally, the string of operators where this A will remain on the right will annihilate psi 0 and become 0, while the ones which have accumulated on the left, they will add up to give me this value n. So then I get this. So what we have got is sort of like a, it's not exactly an, well, you can say it looks like an eigenvalue equation. So if A dagger A is the operator, then acting on psi n, it gives me back n and psi n's. So it tells me the n and gives me back psi n, which means that A dagger A tells me which excited state I am looking at. Okay. Now if you are, so I just spoke about what we did here, but if you're not comfortable with that, I have worked it out afterwards. So if you want to find out a commutator of A with A dagger raised to the power k. So this is a string of k A daggers placed one after the other. Then it can be shown that the commutator value is k A dagger to the power k minus 1. So to see that, let's just take an example of k equal to 2, and we open this up. So A dagger, and then A dagger, A. That is, those are the two terms of the commutator. Then I move this A to the right of A dagger. So to do that, I write A dagger is 1 plus A dagger A. And we have this A dagger, okay. Then I open this up. Then I take A dagger common here. Then I get back a commutator form here, which is 1, and this A dagger remains. So I have 2 A dagger. If I do the same thing with 3 creation operators, I get 3, and the power is lowered by 1. So that's 3 has become 2. And this is just to understand. And if you think about it, this will be the same for any number of A daggers, and you will get n here, which is the number of A daggers that you had started with. Okay. So A dagger A is called a number operator, which tells me the quantum number of the state, so to speak. And if you remember, our Hamiltonian was H is equal to A dagger A plus half H cross omega. So I can simply write that A dagger A as the number operator n. And the energy was written as n plus half H cross omega. So the eigenvalue of the Hamiltonian can also be written then in terms of small n plus half H cross omega psi n. Okay. So similarly, if you have a string of annihilation operators and you want to find the commutator with a creation operator, you can again work it out, and all you will get extra is this negative sign. Otherwise, the relation is totally analogous to the one for creation operators, for a string of creation operators. Okay, some additional properties of this number operator. So now that we have a number operator, let's see what the commutator with another annihilation operator looks like. Then it looks, now this is now easier to derive. So this is a commutator like this. You have A on the left in the one and A on the right. So you can take A common, you get back this commutator, which is now -1. So A dagger is 1, A dagger A is -1. Then with the creation operator, again, you can take this A dagger common from the left, let's say. Then A dagger commutator is 1, so it's A dagger. So what this shows is that if you have a commutator of the number operator with A, you get back A with a negative sign. If you have a commutator with A dagger, you get back just A dagger. Okay. And you can again take it a bit further. So if you have a string of annihilation operators, then so K annihilation operators one after the other, then the commutator gives me minus K, and you get back this whatever was here inside the commutator. And again, for the dagger, you get back plus K. So these are very nice and neat relations, and when you work with these operators and complicated expressions, this is what you will use. You will never need the explicit forms. Okay. So for this proof, okay, anyway, so this is just a small proof of that. That's okay. So now let's look at something else. Let's look at the normalization of the excited states. So what happens? So we're generating the excited states, but are we generating normalized excited states? We have not imposed any such condition. Okay, so we have to check that that everything is fine. So the first excited state is, like we said before, you have a raising operator acting on the ground state. Okay, and now if we use the number operator on psi1, we get back psi1. Then when I use the number operator on psi2, notice that I have written psi2 prime over here because I don't know if it's normalized. And actually I'm a little bit wise after the event, so I know that it will not turn out to be optimized. Okay, sorry, normalized. So when I use n on psi2 prime, okay, psi2 prime can be written as 2 raising operators on psi0. Then this string we can simply replace by a commutator. The reason being that the n acting on psi0 will give you 0, so that term is basically 0. So you can, without any loss of generality, you can replace n a dagger square with the commutator of n with a dagger square. Okay. Then from the above relations, so this is with a dagger, so no sign, the 2 comes forward and you get back a dagger square on psi0. So you have 2 times psi2 prime. Okay, so this is for the number operator, and then the psi2 prime form. Oh, I'm sorry. I think I was going to say something else over here, but sorry. So this is so we'll talk about the normalization a little later. So this just shows that you can actually operate the number operator and get back the eigenvalue. Okay. So this is the normalization part. So yeah. So psi1. So we want to find out the overlaps. So psi1 with psi1 is a dagger psi0 with a dagger psi0. And then you can, so when you move an operator from the bra to the ket, you need to do a dagger on it. So you need to do the Hermitian conjugation operation. So a dagger becomes a when I move it to the ket side. And then again, the logic is the same, that since a will annihilate psi0, I can easily put a minus a dagger a over here. That does not change anything. So when I write that, then I can change a dagger to a dagger commutator. Okay, since I know the value of that, and I know the value of that to be 1, so I get psi0, psi0. So since we have normalized psi0, the first excited state is also normalized. Okay. But when we do the second one, it's again the same principle. So you have a dagger on the bra, and then we shift that to the ket. So we have A now. Okay. Then we move. So we replace the last three operators with the commutator. Okay, because again in the second term, A is to the extreme right and will annihilate psi 0. Okay, so we have the commutator here, and we know the value of this commutator to be 2A dagger. Then 2 here, and I have A dagger left. Again, we replace it with the commutator, and we get psi 0, which is 1, but psi 2 prime turns out to be 2. So it is not normalized. However, once you have found the overlap, it is pretty simple. You just take a square root of it and do 1 by that. So 1 by root 2. So we should put a prime over here. So psi 2 is normalized by multiplying 1 by root 2 with psi 2 prime. Now, if you work out a few more, you will see by analogy that the general normalizing constant for any general excited state, nth excited state, is 1 by root of n factorial. So this is the normalization constant, which we had, which I had just mentioned before, but this is how you derive it. Okay, fine. And again, you can verify that the number operator are acting even on the normalized function gives you the same eigenvalue. So they are also eigenstates of the number operator. Fine. So this is what I had expected to cover in the last lecture, but it spilled over to today. So do you have any questions on this part now before I move to what I had planned for today actually? No? Okay. So then today we will again do the same problem but in a different way. So we will again solve the Schrodinger equation for the harmonic oscillator, but we will not use the creation annihilation operators or raising lowering operators. We will do more or less a standard differential equation solution. Okay. We will not do any tricks with operators. So let's see. So how do you go about that? So this method of solution is called the power series method of solution or the Frobenius method of solution. So we again have the same Schrodinger equation, but we do different things with it. We manipulate it algebraically a little bit. So I have taken the 2 to the right and I have divided throughout by h cross omega. Yeah. So this gives me this common factor over here, m omega h cross by m omega over here. And I change the variable x to zeta. Zeta or xi, what is it called? This is zeta. I think this is xi. I keep forgetting the name of this symbol. Yeah. So this is xi. And what I have done is I scaled x by some constant, root of m omega by h cross. So that will simplify what my equation looks like. Okay. So, but to do that, I need to do some algebra. So x is then root of h cross by m omega xi. And if you take the differential, then dx is equal to root of h cross m omega d xi. Okay, so let's see. So if I do this change of variable, then for the second derivative, d squared dx square of psi, I scale the first derivative, then I get the first d xi, and then I scale it with the second derivative, scale the second derivative, and I get m omega by h cross d squared psi d xi square. So I just introduced this extra factor, which doesn't change something. And when I put this actually back into the Schrodinger equation, we had an h cross by m omega here. So they cancel each other. The second term is simpler, so it's just, so xi, if you take a square of xi, you get m omega by h cross x squared, which is exactly this term. So we write xi square. Yeah, there should be a psi here. Yeah, and on the right we have this new constant, and I just write that as k. And now k is the constant which will tell me what my energies are, okay, afterwards. And then I just move things to the left and right, and we get something that looks simple, okay, simpler than what we had before. But let us see if it is simple to solve. Okay, we want to guess the solution. So to guess the solution, one trick that you employ is you look at the limiting behavior. So here the useful limit is when x is very large or xi is very large. So then you can ignore k compared to xi. Okay. And you simplify the equation even further. So this is sort of like an approximate equation. And the approximate solution from this equation is a standard one that is known. And that is this: a e to the power minus xi square by 2 plus b e to the power xi square by 2. This is the general solution. Now recall that for quantum mechanics, you must always find the allowed solutions, or the physical solutions. And you must discard the ones which are not physical. And the way you do that is you find out the solutions which are normalizable. That is one criteria. There are other criteria, of course, that must fit the boundary conditions of the problem, etc. But in this problem, what we will focus on is the normalization. Okay, that will be enough to give me the physical solutions. So here, from the mathematical solution, we have two terms. One which decays as the xi increases, and one which blows up. So, from your experience with other problems, you must have realized that the wave function must decay at large values of xi or x or whatever is the variable, in order for it to be normalizable. That is quite expected. So, we must discard this second term. Okay. So, this second term blows up. So, this cannot be part of any physical solution. So, they will have this form. Okay, at least in the large x or large xi region. So this is the asymptotic solution. Okay, so my actual solution should sort of move towards this limiting solution. So to do that, we just write a general solution where, in a product form of a general polynomial function, an infinite polynomial function, multiplied by this exponential quantity. Okay. And this general polynomial for this additional function that we use is called, gives the name of the method of solution. So this is the power series for xi. So this is called the power series method of solution. Okay. Now actually a power series in itself is a function that is general enough to represent any function, right? So so you may question me that what is the point of having an additional exponential thing? Won't it complicate matters? Actually, no. The thing is, if you separate out something that is actually an infinite series, then there is a chance that your h psi will turn out to be a simple polynomial. So it's sort of a hope that we will not have an infinite series for h. Okay, that if we separate out the asymptotic region. So that is why we first split it into these two functions, and then we allow h to be general enough so that we don't get any artifact from anywhere. So this form of the function is again general enough to represent anything that psi may be. So there is no approximation involved here. Okay. And we write this in a shorthand summation notation. So j equal to 0 to infinity aj xi to the power j. Okay. Now we will use this functional form in the Schrodinger equation. Okay. So let's see. So when we do the first derivative of psi with respect to xi, so I'm integrating by parts. So this part is dh d xi, and the function remains as it is outside the bracket. Then when I differentiate e to the power minus xi square by 2, I get minus 2 xi by 2, and h remains as it is. And again, you get back the exponential form, so that can be taken common, and you get the first derivative of psi with respect to xi. Then when you do the second derivative again, you do it piece by piece, of course. Okay, you take second derivative here, then you leave this alone, take another derivative of this factor, okay, and then you get this term. And when you look at the second term here, then the first you take the derivative of this product. Again, this must be done by parts afterwards, and you again have a e to the power minus xi square factor. So this you can sit and work out yourselves. It is simple enough, and you get the Schrodinger equation in terms of h and xi over here. Sorry, this is the second derivative, and then you can write the Schrodinger equation, and then you have these two exponentials which you can remove, and you also have and then you move everything to the left. You get something that looks quite decent, actually. Okay, but now we need to know the derivatives of h, which we have assumed to be a power series. So let's do the derivatives of h with respect to xi. So the first derivative is simple. You don't need to think much. You have the summation form. Then if you take a derivative of every term, you will get this factor in front, j, and the power will be reduced by 1. So if you do a term by term differentiation, they can again be grouped together as a summation. Okay. Now when you take a second derivative again, from every term which has a j, it will be associated with a xi which has a power of j minus 1. So j minus 1 will come in front, and xi will take on the power j minus 2. So here actually you don't need to expand things to take a derivative. But be warned, taking derivatives of summations, normally you cannot, I mean in general you cannot keep the summation all the time. So in this particular case it is simple enough that it looks like you can just take a derivative of this sum form. But sometimes you have to actually open it out and take the derivative and then again regroup it into a summation if you can, or sometimes maybe you cannot also. That is also possible. Okay. So here you can keep the summation, so I did not have to expand the whole thing. So it looks like this now, the second derivative. But when we put it back into the Schrodinger equation, I would like my xi's to have the same power. So I want everything to be written as xi to the power j. So I shift my j to j plus 2. So if I shift my j to j plus 2, then the summation changes from j equal to 0 to infinity to j equal to minus 2 to infinity. If this confuses you, then maybe you can think of it as changing your variable j to I plus 2, some other variable I plus 2. Then I is equal to j minus 2. So j equal to 0 means I equal to minus 2. So you can write I equal to minus 2 to infinity. Okay, then j becomes I plus 2. So ai plus 2 into I plus 2 into I plus 1 into xi to the power I. And in the next step, then you can again change the variable I back to j. So you can think about it like this. But normally people do it in one step, where you just say that you shift j to j plus 2. And you put it again back into the Schrodinger equation. So here, what do we have? We have the second derivative, which is just this term now, okay, with the xi to the power j, which I have kept common over here. Then you have the first derivative, which has xi to the power j minus 1, but there is a xi here. So this xi becomes xi to the power j again. And you have the minus 2 then, j, aj. And k minus 1, h. H is simply the guess that we took. So aj, xi to the power j. So now we have been able to take xi to the power j common. Okay, one more point here. So what happened from here to here? So j, the summation had changed to minus 2 to infinity. But again, I have changed it back to 0. How did that happen? So basically, if j is minus 2, then this factor is 0, so the term disappears. If j is minus 1, then this term becomes 0 and the full term disappears. Okay, so the non-zero terms start from actually j equal to 0. So we can discard the first two terms as it is. Fine. Now we have this Schrodinger equation, which looks very different from the Schrodinger equations that we know, but we have just replaced things step by step. So yeah, it still contains the same information. And this looks more like a polynomial equation. And as you know, since you have different powers of xi, every coefficient, so for every power, the coefficient must be 0. Okay? There is no other way, because here we are not, remember, solving for values of xi. We are solving for values of aj. Okay. So this is an equation for all xi. Then if every coefficient is 0, then we have this relation which can be rearranged to give me a recursion formula. And the recursion formula looks something like this, that aj plus 2 is some factor in terms of j and the constant k into aj. So if you know some j, then you can find the value of the coefficient for j plus 2. And these are the coefficients of the wave function. So this is the equation that you need to solve in order to find the wave function. So from here, what you can directly conclude is that if I know A0, I can find A2, A4, A6, etc. If I know A1, on the other hand, I know A3, A5, A7. So basically, I have two unknowns. So two arbitrary constants, A0 and A1. And once I can find the values of those, the other coefficients are known. And once the other coefficients are known, my wave function is known. Okay? And so there is a natural split between the odd powers of xi and the even powers of xi. So h xi can then be written as a sum of the even power of some function with the even powers and some function with the odd powers. Okay. So we have found some way. So we have not found an explicit solution yet, but it looks hopeful. Okay. Also remember that this was a second order differential equation to start with. So having two arbitrary constants is normal. That is what you would have expected, and that is what we have here. So that is a good thing. Okay. So now that we have some relation for finding out the the coefficients of psi in H psi, let's look at the total wave function again. So the total wave function is H psi multiplied with e to the power minus xi squared by 2. Fine. And here we have the recursion relation. So if we have very high powers of j in my expansion for H psi, then my recursion relation can be simplified a little bit more, and the energy dependence can be got rid of, and you get 2j aj by j square. So I have ignored 1, 2 and 1 minus k, and that gives me 2 by j aj. So the ratio of the next coefficient that you can get and the one before is then 2 by j. So this ratio keeps on decreasing as you go to higher and higher j. So a j plus 2 does become smaller. However, it does not become, but it does not decay fast enough. Okay. So how do we know that? So we can see that it is decaying, but there's something else we now want to look at. So how fast is it decaying? So to do that, we look at how you express some e to the power u square function. Okay. So if you look at e to the power u square, then the series expansion is sum over n equal to 0 to infinity 1 by n factorial u to the power 2n. Okay. Now if I change the variables from n to j, where j runs only over the, let's say, the even numbers, then I can write j equal to 0 to 4 up to infinity, and n I write as j by 2. And then 2n becomes j. Then the coefficient for uj becomes 1 by j by 2 factorial. So that is like, let's say, cj. So, and then cj plus 2 by cj turns out to be j by 2 factorial by j plus 2 by 2 factorial, which is 1 by j plus j by 2, which is again 2 by j. So if you have an infinite power series which obeys this recursion relation, that is basically identical to a e to the power u square function. And e to the power u square, as you know, is basically a diverging function if u tends to infinity. So basically, this expansion is not good enough. Okay. So what you need is basically the polynomial to be not infinite. So it must truncate at some finite value of j. Okay. So at some point, after some point, a j plus 2 must become 0. So I cannot have an infinite polynomial because that is as bad as an exponential, positive exponential. And how does this become 0? This becomes 0 only if k is equal to 2j plus 1 for some value of k, for some finite value of k. So now what is the argument? So that tells me that if I want to have a normalizable solution that obeys the recursion relation that is identical to the Schrodinger equation, my energies or my allowed energies can only be integers and have the value 2j plus 1. Or okay. So that is a very powerful conclusion and a very unbelievable conclusion. But that is how this works. That the only energies for which you can get normalizable solutions for a harmonic oscillator are those where k is equal to some integer of the form 2j plus 1. Okay, so there will be some value of j such that 2j plus 1 is equal to k. So let's go forward a little bit more and think about this argument a little bit from different angles. So if we are working with arbitrary values of K and hence energy, then the series for H will never truncate. Okay? However, if K is 2J plus 1 for some finite value of J, let's say we call that N, then A, J plus 2 will be 0 for all J's greater or equal to N. Okay? And then the series will truncate at this value. And once you have a truncating series, there is no problem with things blowing up with increasing xi, with increasing values of J, sorry. Okay. So, like I said, the only normalizable solutions thus correspond to integer values of K, which is 2J plus 1. The requirement of normalizability thus quantizes the energy. So this is again, so we are back to a similar argument as in the case of our, was it? No, it wasn't particle in a box. It was the free particle, right? Where the requirement of normalizability quantized my energy. Okay? So this is the same here, but in a it comes in a different disguise. Okay, so here it comes from the recursion relation. So that is really a very fascinating aspect of quantum mechanics. So what you want to do is basically the same. You want to solve the Schrodinger equation given a potential. But you tweak the potential a little bit and then the way of solving the thing changes entirely. And your syllabus is also designed to actually show you very diverse methods of solution so that you can mix and match them when you come across your actual research problems or whatever. Okay, so then let me repeat this again. That if K is such that it is 2n plus 1 for some value of n, then the power series truncates at j equal to n. So you start with j, if you're looking at the even solutions, then j equal to 0 to 4 up to n. So you will have these terms. So n by 2 terms in that expansion again. Similarly for the odd solution. So if n is odd, then the odd series truncates. If n is even, the even series truncates. But then what about, but we had said that the general solution is even plus odd. So then if n is even, then the odd part can still diverge. And if n is odd, then the even part can still diverge. Okay. So this is an indication that, it is an additional requirement that for normalizable solutions, the solution must be either even or odd. It cannot be a combination as we had proposed before. So although mathematically again the general form can be a sum of odd and even, the physically allowed ones will either be odd or be even. And let's get back to then the allowed energies. So the values of K that we want are 2n plus 1. So the values of energy then, allowed energies, are then En 2n plus 1 h cross omega by 2, or just divide by 2 when you have En equal to n plus half h cross omega. So this is a very simple now energy expression for the various states of my harmonic oscillator. So if n is equal to 0, then you have the ground state, and the ground state has the energy half h cross omega. This is also called the 0-point energy. So the lowest energy for the harmonic oscillator is not 0 here. It is half h cross omega. If you remember, for other particles, the lowest energy was always 0. But there is a 0-point energy for a harmonic oscillator problem. Okay, so we don't have time anymore. So we have actually finished right on time today. That's good. So next class we will continue with this harmonic oscillator problem. Okay, I hope you have all submitted or are soon to submit your assignment 3. And I had promised to give you an assignment over the vacations, but I did not manage to upload it. So I will give it to you after we finish the harmonic oscillator problem. Okay, it will be on the harmonic oscillator. Fine, and I will probably need 2 more classes, and I will speak to Professor Pal about taking over after that to teach you the hydrogen atom problem, which is the last one. And the rigid rotor, which was also part of your syllabus, because we have fewer classes this year, we are not going to go through that. Okay, so that is out of syllabus now. The rigid rotor problem. Okay. So thank you, everybody. Recording.